Alright, today's lecture, Chapter 3, Section 4. We're going to be talking about linear speed and angular speed. Alright, so I want you to start thinking about, we're still talking about something in motion though, and we're talking about, how fast an angle is moving around a circle or how fast a specific point is moving around the outside of a circle. Okay? So for us, linear speed, alright, we are keeping track of how fast a point on the outside of a circle or a disk is rotating. Okay, very, very important for us in engineering world and things like that, where we have a motor. We want to keep track of how fast that motor is turning over. So we want to keep track of the RPMs, or the revolutions per minute. So we have motors that are constant speed motors. So if it's 1700 RPMs, it should be always doing 1700 RPMs. All right, or we might have a variable speed motor that's, we're able to control the different speeds, all right? But for us to calculate that, we have to have a point that we maintain. So your vehicle uses something like this as well, so that you know how fast you're going. So when you look at the speedometer, it knows if you're going 50 miles an hour, 100 miles an hour, those sort of things. So make sure we draw this down. So point P, all right? Very, very important on here. Okay, we're talking about how fast it's moving around the outside of the circle. Remember, that is linear speed. Okay, linear speed. If we're talking about the point. Okay, so how do we calculate speed? It's a velocity, right? Speed is a velocity. And how do we calculate that? For all the math that you've ever learned, it's always distance over time. Speed is always distance over time. So for us, we're going to say V equals S over T. All right, so velocity equals arc length divided by time. So we're going to calculate the actual arc length of where theta is at that particular point in time. All right, so make sure you guys got these written down as we go through. So as point P moves along that circle, right, that ray OP rotates. I really just want you to think about a clock hand rotating around. That's really all we're kind of keeping track of, right? The arrow at the end of like an hour hand or a second hand or a minute hand doing the same thing. Okay, we want to keep track of the theta. The theta is the angle speed, how fast the angular speed is going. We always talk about angular speed, we're talking about omega. Okay, so omega is our angular speed. Theta is the actual angle, all right? So it's theta, or the angle, divided by time. That's our angular speed. Really, those are the only two equations we need. We do need S equals R theta, all right, from a previous section that we did when we calculated arc length. But other than that, it's really just manipulating these two equations between angular speed and linear speed. And once you guys get those down, all right, this should come pretty natural to you. Okay, so these are the equations that we are going to use. So I would make sure that you pause the video, you write these down, and then when you're doing your assignment, you have like a little note card or your notes next to you with these equations. Because really, it's just a matter of, what am I given in the problem, what am I asking for, and which one of these equations suffices. All right, but anytime we're talking angular speed, we're always talking omega, and it's always theta over time. Linear speed, we have a few more choices, right? It's S over T, which is arc length over T. The middle equation, R theta, is just rewriting S as R theta, right? That's the arc length. And then we can also replace that middle equation where we have theta over T. We can replace that with omega using the angular speed on the left-hand side. So we have to know how to be able to go back and forth between these given equations here, all right? So let's take a look at an example. It says, suppose that point P is on a circle with a radius of 10 centimeters and ray OP is rotating with an angular speed of pi over 18 radians per second. We want to find the angle generated by P in 6 seconds. Okay? So, you got to think about, what are we given here? We're given R, which is 10. Okay? We're given our angular speed, that's our omega, right? Is pi over 18, and we want to find theta when time, or t, is equal to 6. All right, so we got to choose the right equation here. All right, there is a part B that's associated with this as well, but so let's choose the right equation. All right, right now we know that omega is theta over t. All right, that's given. We know what t is and we know what omega is. So we substitute those values in to solve for theta. So when we do that, omega is pi over 18 is equal to theta over t, which is 6. So we get this equation here. We get pi over 18 equals theta over 6. Well, theta is being divided by 6, so we have to multiply both sides by 6. So we're going to get 6 pi divided by 18, or we end up with pi over 3. All right, when we simplify that down. So theta, okay, is pi over 3. That's the angle that at time in 6 seconds we get a angular speed omega of pi over 18. All right, so that answers part A. We're solving for theta. Theta is pi over 3. All right, so part B says find the distance traveled by P along the circle in 6 seconds. Now the distance traveled, you should be thinking linear speed. Okay, linear speed. So we have to have the V equals one of those equations that were on there before, okay? But we have to find out what the arc length is. So S equals R theta. We just calculated theta in the previous part, in part A, right? That's the pi over 3. And then our radius was given at the beginning of the problem as 10 centimeters, okay? So we were given this. We need the S, right? Because why? Linear speed or velocity is what? Distance over time. We're calculating the arc length distance S here, and this is the last piece of the puzzle because we already know time is 6 seconds. Okay, so we don't have to even keep track of the 6 seconds because it worked through in part A. All right, so part C, find the linear speed of P in centimeters. So this is where we actually find the speed. So the distance itself is just S equals R theta. Okay, that's the arc length piece. Part C, we plug into V equals S over T. All right, so we're going to take 10 pi over 3 divided by 6. Okay, so when we do that and we simplify the fractions and we work down, we end up getting 5 pi over 9 centimeters per second. Okay, so we kind of broke this down. Okay, so part A, we found theta using the angular speed. Okay, if theta, omega equals theta over t, we were given omega and t and we solved for it. Here we had to find the distance, okay, so that's the arc length. We found theta, so that's the theta we used, and we were given 10 for the radius. Okay, then once we knew the distance traveled s, we were able to calculate the linear speed, which is the velocity, which is s divided by time. Okay. All right, let's do another example here. We want to find the angular speed of a pulley. All right, so a belt runs a pulley with a radius of 6 centimeters at 80 RPMs, revolutions per minute. Find the angular speed of the pulley in radians per second. So what you should be thinking in your head, all right, angular speed, that's omega theta over t. What do I have that's going to help me get to my theta? Well, I got my revolutions per minute. So we need to break that down. And remember, we're in radians. So we need to know that every revolution is 2 pi, right? That's the complete distance around a circle. So that happens 80 times in 1 minute. So we have to take 80 times 2 pi. So we're getting 160 radians per minute. And we know there's 60 seconds in a minute. So omega is going to be 160 pi divided by 60, or 8 pi over 3 radians per second. Okay, because the question asked us what? Per second. So we had to divide, that's our time. Okay, so we 160 pi, right? That's our RPMs, that's our theta, all right, as it goes around. So now we want to find the linear speed of the belt. Okay, the linear speed. So first we have to find the total distance, right? So V equals R omega. We have R, we have omega. We don't have to use that equation, the other equation from before. We can use what we found in part A. All right, since we know omega is 8 pi over 3, we can multiply it by the radius, which is 6. So we end up getting 16 pi equals 50 centimeters per second. So we're really just taking a look at these equations. I'll bring them back up on the screen here. It's really, which one of these equations fits what we have. So linear speed, based on what we had the first example, we had to use S over T. So we used the first linear speed equation. The last example we just did, we already had omega, which was theta over T. So we found linear speed using the bottom equation, V equals R omega. So this is where, I said, make sure that you have these next to you and make sure based on what you're given, all right, pick the equation that makes the most sense to you to apply. All right, last example here. We have a satellite traveling in a circular orbit, 1,600 kilometers above the surface of the Earth. Okay, Earth takes 2 hours to make an orbit. The radius of the Earth is approximately 6,400 kilometers. So we got a nice little picture here. So make sure that you look at the 6,400. That's the radius of the Earth, right? And then the satellite is 1,600 kilometers above the Earth. So what you got to remember, if we're basing it from 0, 0 being the center of the Earth, you got to be very careful about this problem. What is your radius? Your radius is going to be the 6,400 plus the 1,600. So be very, very careful here. All right, so we're going to approximate the linear speed of the satellite in kilometers per hour. So this goes back to choosing the right equation. Choosing the right equation. So remember, linear speed is some sort of distance over time, or S theta over T, or so on and so forth. So which one do we pick here? But like I said, the first part, most important part, keeping track of what the true radius is on this. We're going from the center of the Earth, so we got to combine those to get 8,000. So now we have to find the distance, right? S equals R theta. How do we know theta? It's a circle. So one orbit is 2 pi. Okay, so theta goes around 2 pi, right? 360 degrees if we're talking that. So S equals R theta. So we're going to take 8,000 times 2 pi. That's going to give us 16,000 pi kilometers. Okay. So the last part of this, though, is since it takes 2 hours to complete the orbit, okay, and what we just found is one distance, 16,000 pi kilometers. That's one time around. So we know that it takes 2 hours to complete that. We actually have to do a little bit more math behind that and cut it in half, right? So one complete orbit is 16,000 pi kilometers, but we know it takes 2 hours, so we got to divide that by 2. So 16,000 divided by 2 is 8,000. So we end up with 8,000 pi, which is approximately 25,000 kilometers per hour. So last part of this, I want you to approximate the distance the satellite travels in 4.5 hours. So how many orbits is that, right? It's 2.25, right? 2.25 orbits. So you got to think about that. So as we do this problem, okay, you just have to take S equals VT. So distance equals rate times time, right? Distance equals rate times time. You've learned that before. So S equals VT. Not a new equation, right? We just used it in terms of V equals S over T before. So this is S equals VT. It's distance equals rate times time. Something you've known since like 5th or 6th grade. So velocity is 8,000 pi, right? We know that that's how fast it's going. And then we multiply it by 4.5. So we get 36,000 pi, or 110,000 kilometers. Okay, so that's the end of the examples. I really want you to focus on this piece and understanding which equation do I choose based on what's given to me. All right, I've come back to this one a couple of times. Really understand the difference. How fast are we going, or how fast is a specific point going around something, and how do linear speed and angular speed relate? It really comes down to understanding these equations and choosing the right ones that fit the problem that you need to solve. Alright, so this is it for chapter 3. We'll be taking tests fairly soon. Make sure that you got good notes going on. Make sure you email me with any questions, and we can Zoom or something like that if you need to review some things.